Don't do that. Think about this. Section 1 is called Permutations and Combinations. All of the stuff that we have done leading up to this point, working with dice and cards. We threw darts, but we haven't had time to take a look at the darts yet. There's more stuff that we will do to collect data. But for right now, we've done enough to where we can handle this section. So what we're doing is counting the possible permutation and combinations for a scenario. We're going to be using the fundamental counting principle to find the outcomes. We've already learned the fundamental counting principle from the stuff that we've been doing. So hopefully you have a good understanding of it. Here is the definition of the fundamental counting principle right here. Very formally, if event M, capital M, can occur little m ways, so think of that as a die. If I can roll a die, me rolling the die would be event M. How many ways can I roll a die? 6. So that would be 6 ways, okay? So event M can occur in little m ways, followed by event N that can occur in little n ways. So if I roll a second die, that would be event N. It can occur 6 ways, right? Then, event M followed by event N can occur in m times n ways. That's the fundamental counting principle right there. I take those two numbers that I just said, 6 and 6, and I multiply them together and I get 36. So to roll 2 dice, there's 36 ways for rolling 2 dice. Dealing a hand in poker. If I want to know how many ways I can deal 2 cards to you in poker, then the fundamental counting principle says, take the number of ways that I can do event 1 times the number of ways that I can do event 2. How many ways can I do event 1? Event 1 would be me dealing that first round of cards. How many ways can you get that first card? 52. How many ways can you get that second card? That's event N. 51. So you'd have 52 times 51, which we've done enough. We know it's 2,652. Okay, so that's not a fraction bar. That is a position holder, and I was about to explain that. When I'm doing problems like this that involve the fundamental counting principle, I'll put little dashes down to show me all of the positions that things can be. Okay, so like for example in this problem, if all zip codes use 5 digits, how many zip codes are possible? Well, in a zip code, like we have 82426, right? That's 5 digits. In a zip code, there are 5 positions. 1, 2, 3, 4, 5. I'm going to multiply the number of ways that each one of those positions can occur. So how many digits do we have that can go in that first position? There are 10 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, but also 0. So there are actually 10 digits that can go in that first position. How many digits can go in the second position? 10. How many digits can go in the third position? 10. And the fourth position? 10. And the fifth position? 10. So the fundamental counting principle says that I can take each one of those and treat them like events. Event 1 would be position 1 on the zip code. Event 2 would be the second position on the zip code. Event 3 is the third position on the zip code, and so on. Now I can take each one of those and multiply them together. What is 10 times 10 times 10 times 10 times 10? No. 100,000. So there are 100,000 ways to make a zip code based on that information. And that's how you use the fundamental counting principle. So anytime you have events that are occurring together, draw out some dashes for each one of those events. Figure out how many ways each event on its own can occur, and then multiply those numbers together. We have some notation to talk about. It's called factorial notation. You may have seen this symbol before. It's an exclamation point. An exclamation point is read factorial in math. So for example, if you see 5 with an exclamation point after it, it means factorial. You would read it as 5 factorial. And all that means is you take the integer that you're looking at and you multiply it times each sequential integer that's lower than that all the way down to 1. So 5 factorial turns into 5 times 4, times 3, times 2, times 1. And then you'd multiply that all out. 5 times 4 times 3 times 2 times 1 is 120. Before I go on with the factorial stuff, I want to go back to poker real quick. We did 52 times 51 for 2 cards being dealt to you in Texas Hold'em. But what if I'm dealing out 5 cards in 5-card draw? How many ways can that occur? Well, there's 5 cards being given to you. 1, 2, 3, 4, 5. How many ways can I get that first card? 52. Once I have that first card, how many ways can I get that second card? 51. And how many ways can I get that third card? 50. And how many ways can I get that fourth card? 49. And the last card? 48. 52 times 51 times 50 times 49 times 48. That's a really big number. Yeah, it's like 300 and something million, right? $311,875,200 ways to deal 5 cards in 5-card draw. A lot more ways than 2,652 ways in Texas Hold'em. But notice how I did that. It's a fundamental counting principle. I drew out the dashes for each card that I was receiving. Each one of them is treated as an event. Event 1 was getting that first card. Event 2 was getting that second card, and so on. How many ways can I get that first card? How many ways can I get that second card? And so on. Multiply all those numbers together to get your total number of ways that can be dealt to you. Now notice what's happening here. 52, 51, 50, 49, 48. If I kept dealing more cards, we would wind up with 47, 46, 45, and so on. Okay? That's where this factorial notation is starting to come in. 5 factorial was 5 times 4 times 3 times 2 times 1. We get 120. To evaluate a factorial, start at the number that you're given, multiply it times each sequential number less than that, all the way down to 1. So 4 factorial would be what? 4 times 3 times 2 times 1, which is 24. 8 factorial would be what? That's right. And what do we get there? 40,320? Okay. Go ahead and do 32 factorial. So for 32 factorial, we wind up with 32. No, I'm just frozen. Okay, there we go. Oh, it's frozen again. 32 times 31 times 30 times, we wind up with times 3 times 2 times 1. So I'm skipping over all the numbers in the middle. Sure. When you multiply all those numbers together, you get 2, 6, 3, 1, 3, 0, 8, 3, 6, 9, 3, 3, 6, 9, 3, 5, 3, 0, 1, 6, 7, 2, 1, 8, 0. Is that it? No, there's more. 3 more? 1, 2, 3. All right. There's your answer. Well, I don't even know what that is. Let's see. Thousands. So 100,000, millions, billions, trillions, quadrillions, quintillions. Nobody even knows what the heck that is. It's an absolutely enormous number. Okay, how about 8 factorial divided by 5 factorial? I want to write this one out because I want to show you what happens. 8 factorial is just 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now we're dividing by 5 factorial. So 5 times 4 times 3 times 2 times 1. What happens? There's fancy ones here. We have a 5 divided by 5. Those are gone. A 4 divided by 4. Each one of these is turning into a 1. 3 divided by 3. 2 divided by 2. And, of course, 1 divided by 1. So we're just left with 8 times 7 times 6. That is an easy number to do on your calculator. What do we get? $336. So when you're dividing factorials, if you write them out, a lot of that stuff is going to cancel out, and then it makes your math a little bit easier to work with. And of course, there's a button on the calculator that will let you do factorial easily without having to write all that junk down. So on your calculator, go to the calculator portion. You asked me if there was a trick. You didn't ask me if there was something on the calculator that would let us do it easier. So let's do 8 factorial. So I'm going to type in 8, and then we just have to figure out where. Why are you doing that to me? Delete. You just have to figure out where the exclamation mark is. It's down here at the bottom. You see the little question mark exclamation point? That's the one we want, and then we're going to select the exclamation point and then hit enter, and it gives us 40,320. Exactly what we expected. Now we can also do math like that last problem, 8 factorial divided by 5 factorial. So let's go ahead and do that. Type in the 8 and then factorial and divide it by the 5 factorial. And press enter, and you get 336. So the calculator will do factorial for you. In fact, any graphing calculator will have factorial on it. Scientific calculators also have factorial on them. You just have to learn how to use them. But here you go. You can do the homework using the calculator involving factorial. Any calculator that's worth its weight will have factorial on it. So you don't have to specifically use ours. Okay, the next thing we're going to be talking about independent and dependent events quite a bit. For right now, we're talking about dependent events. It says for dependent events, sequential events depend on the outcome of previous events. So, for example, let me see if I can illustrate the difference between independent and dependent. If I have 2 dice and I roll them, is that going to be a dependent situation? Does the outcome of one die depend on what happened with the other die? No, it doesn't. Okay, so that's not a dependent event. But if I deal you one card and then I deal you another card, is that going to be a dependent event? Yes, because the outcome of the second one depends on what you got for the first one. That is dependent. So that's what that means. For example, you have 6 homework assignments to complete. How many different ways can you complete them? Well, first of all, this is a fundamental counting principle problem. We have 6 different homework assignments. Each one of those is its own event. So I'm going to draw 6 dashes. 1, 2, 3, 4, 5, 6. All of these dashes are going to be multiplied together. And now I just have to think, I have to complete these homework assignments in some sort of order. How many different ways, or how many different homework assignments do I have to choose from to do my first homework assignment that I have to do? I have 6 different assignments to choose from. Now, once I complete that homework assignment, how many assignments do I have left to choose from for my second homework assignment that I do? 5. And now how many assignments do I have left to make my third homework assignment complete? 4. And then how many homework assignments are remaining for my next one that I do? 3. And how many are left for my second to last one? 2, which leaves me with exactly 1 remaining to do for my last homework assignment. What does that look like? It looks like factorial. This is actually 6 factorial. So on your calculator, you could quickly type in 6 times 5 times 4 times 3 times 2 times 1. Maybe you could do some of this in your head and say, well, that's 30, that's 8, so that's 24, so 30 times 24. Or you could type in 6 factorial. What do you get? 720 ways. So notice the power of drawing this little picture with the dashes when you have several events that are going to be multiplied together. It's an incredibly powerful tool here. So make sure that you know how to use that, because it's going to come up all the time. All right, how many different ways can a deck of cards be arranged after shuffling? A lot of ways. 52 ways? 52 factorial ways. That's right. Because that top card in the deck can be one of how many cards? 52. The next card in the deck can be one of how many remaining cards? 51. The next card in the deck can be one of how many remaining cards? 50. On down for all the way until we get back all the way down to the last remaining card. So times 1. That is 52 factorial. And what is that number? 806-581-759-438-7-857-1-660-64037. I don't even know where I'm at anymore. Let me move my cursor over. I'm looking for 64037. Okay, there we are. 6697. I need to go down to the next line. 528950544088832. 77824, and then a bunch of zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like 12 zeros. That is how many different ways a deck of cards can be arranged after shuffling. I have no idea what that number, I don't even know how to read that number, it's so big. But the interesting thing here is, since the invention of a deck of cards, every person in the world could shuffle a deck of cards and then record how that deck of cards had been arranged. Every single person in the world accounts for here. Every single person in the world could spend their entire lives from the day they're born to the day they die, starting right now, shuffling decks of cards every 1 second, and they still would not be able to come up with or have shown all of the possible ways that a deck of cards can be arranged. Which means you can say with pretty much 100% certainty that you can take a deck of cards and shuffle it and hold it up and say that you can say with almost 100% certainty that no deck of cards in the history of cards has ever been shuffled exactly that way. Pretty interesting. That number is so huge that you can actually say that.